So now I'm going to use KNN, which stands for K nearest neighbor, to perform a classification task on iris dataset. So first thing I'm doing, I'm importing my necessary libraries. I'm importing my train, test, split. This one is responsible for splitting your data into training and testing. I'm also importing standard scaler. This is responsible for scaling your data. In KNN, you need your data to be scaled in order for it to work effectively. Then I'm also importing K-neighbors classifier. This is the core library that is responsible for classifying your points based on KNN algorithm. I'm also importing accuracy score. This is responsible for checking your accuracy, how good your KNN is doing based on the test data. I'm also importing label encoder. This is responsible for encoding your labels. The dataset that I'll be using is Iris dataset, this one right here. So it has four features: sepal length, sepal width, petal length, and petal width. And the last one is your label species. And there are three different types of species over here. Setosa is one of them. And as I scroll down, you're going to see the other one, which is versicolor. That's the second species. And let me scroll down a little bit more. And now you're going to see the third species, Virginica. So you have three different species in this data set. Or in other words, you have three different labels. So your problem formulation is this: design a machine learning model that would predict the label, whether it's a Setosa, Virginica, or versicolor, of a data. Sepal length, sepal width, petal length, and petal width. This would be given to you. Based on this information that's provided to you, you have to predict what type of iris flower that is. That's your problem formulation. Now we perform data collection. So here, my CSV file is datairis.csv. I'm reading the CSV file using pandas, and I'm printing first few records of that. And these are some of the first five records of the data iris CSV file. And you can see that this is sepal length, this is sepal width, petal length, petal width, and species. And now we do data labeling. In this particular instance, the data is already labeled for us. You have species, this is your label, and all the labels are already given to you. So you don't have to perform any data labeling over here. EDA, you can also do EDA over here. In this session, I'm not going to perform EDA because this session is about KNN. Now we do label encoding and data split. So let's separate our feature X and label Y. So in this case, my feature X would be represented by X, and I'm taking all my feature columns: sepal length, sepal width, petal length, and petal width. These are my features, and my label is species right here. So I'm printing my X and Y, and in this case, when I run this, it prints out my this feature space right here. This is my feature space, and there are actually 150 rows and 4 columns. And same thing with your Y, which is my labels. And you can see that there are 150 rows in total. Okay, now let's encode our labels before we do splitting. So I have a label encoder. Passing in my Y, which is my species, this one right here. So it's going to take all these parameters: Setosa, 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 Virginica, versicolor, all those colors, and it's going to convert them into a number. And I want to know what type number those are and what is the label that is assigned to them. So in this case, I'm also printing those information out. So when I run this, it tells me it has actually recognized three classes: Setosa, versicolor, Virginica, and the label it has assigned is 012. All right, then I split my data into training and testing. So I'm invoking my train test split method. I'm passing my feature space, which is my X. I'm also passing my target variable. In other words, my labels, in this case, is Y encoded. And I'm also specifying my test size. 30% of my data should be for testing. Then I'm printing the shape of my training data set. I'm also printing the shape of my testing data set. So when I run this, it gives me there are 105 record or instances for training data, and there is 45 for testing data set. All right, now let's make sure that we have a balanced target variable in our training data. So I'm actually using this NumPy, and I'm using this inbuilt method called unique, and that's going to return the values and count for each one of them. And after that, I'm just doing zip. I'm zipping these values and count, and I'm printing my value count. So it tells me that for 0, there are 31 records available. For class 1, there is 37, and for 2, there are 37. That seems like to me pretty balanced. 31, 37, 37. All right, that seems to me pretty balanced. And now we do data pre-processing and feature engineering. So in this particular step, I'm going to be performing only standardization. So I'm using standard scaler, and I'm passing in my X train to this, and then I'm also passing my X test. And after that, I'm printing my original data. I'm just printing just one value just to show you how my original data looks like and how my scale data looks like after the transformation. So when I run this, you can see that the original data is 5.5, 2.4, 3.71, and after scaling, it has turned to these values right here, these four different values. And then I do modeling and training. So in this particular instance, I'm using KNN classifier. So, and I'm choosing my k equal to 5, and I'm passing my number of neighbors as k, which is my 5, and then I train my model right here. So let's see, let's run this model, and it gets trained pretty quick because this is only small data set, only like 150. And now let's check our model performance and let's evaluate how our model is doing. So let's start with a simple sample. So this is a simple sample I took from the X training dataset. And in this case, this dataset I took from our data file, and the actual for this one is Satosa. And just to show you, these values are right here. So the first one I took was this one right here, this right here. This is exactly this one. So I just put this copied and paste over here. Same thing with my versicolor. I took versicolor from the file, and I also took one from the Virginica just to see if it's going to make a right prediction. And then I'm converting into data frame. I'm scaling it. Then I'm asking KNN to make a prediction. It makes a prediction, and then I'm decoding my prediction. After that, I'm printing my prediction. I'm also printing the predicted class. And in this case, you can see it predicted 0, 1, 2. And 0 is Satosa, versicolor, Virginica. So this one was Satosa. It predicted Satosa. The second one was versicolor. It predicted versicolor. And the third one was Virginica. It printed Virginica. Great. So this is working fine. Now let's make a prediction on the test data set. So in this case, I'm passing my X test scaled, the scaled version, and it makes a prediction. Then I'm putting all the results in a data frame. So in the data frame, I'm putting my actual encoded. I'm also putting in my predicted encoded. I'm also putting actual label and the predicted label. Then I print my results right here. So after I print my results, you can see this is the answer right here. So let's look at a few of the records. Let's look at this one. In this case, the actual was 0, and the this is your index. Your actual was 1. Sorry, let's come over here. Yeah, actual is 1, predicted is 1, and the actual label was versicolor. The predicted label was versicolor. Your actual was 0, your predicted is 0, and this was Satosa, and this was predicted as a Satosa. So this is how you read this. Okay, and you can see they're all matching. All of them are matching. Great. Now let's look at the performance of the model. Now we can test this by using inbuilt. There's a function we call accuracy score, and I'm passing my Y test and I'm passing my Y prediction. It's going to compare how many are different and how many are not, how many are same or how many are not same. Based on that, it's going to give you an accuracy score. So when I run this, it gives me an accuracy score of 100%. And the final step is hyperparameter tuning. Well, in this case, there's no need because the model is giving me 100% accuracy.